Hi, good afternoon. I'm Matthew Larkin, and as Simon mentioned, today's presentation relates to lithium battery safety. So we'll be covering the basic construction of the cell, example tests that you would perform to show compliance, and safety mechanisms that are featured in the cell and the battery pack. The lithium battery can be traced back as far as 1912 due to the work of the chemist Gilbert Newton, but it was not until the 1970s when lithium primary batteries became commercially available, and another 20 years further in the 1990s when secondary lithium-ion batteries became available through the work of such people as John Goodenough and his contemporaries. So why do design engineers choose lithium-ion to power their products? One reason is energy density, which is a measure that can be made to compare battery chemistries to partly aid designers to choose the appropriate battery for application, the correct chemistry. Basically, the two main parameters for determining this are gravimetric energy, which is calculated by the capacity of the battery divided by the weight of the battery, volumetric energy, which is calculated by the capacity of the battery divided by the volume of the battery. Typically, for a portable application, such as a mobile phone, you're looking for a high energy density, which means the battery's got the ability to hold energy and have a long run time, which results, hopefully, in a lighter, smaller battery compared to a battery of another chemistry of a similar capacity. Power density is another key performance indicator, and that is related to energy density and is the ability of the battery to deliver power on demand, which is advantageous in power tool applications and also transportation. These parameters tend to be optimistic, but nevertheless they give an indication of the battery. But other important parameters are needed to be considered too, such as battery life cycle, which basically means after your battery is being continually charged and discharged, how long does it retain that capacity or charge before it becomes not fit for purpose? And if you look at the graph, you can see that generally the better energy density will be moving up and towards the right of the graph, meaning it's smaller and lighter, which you can see lithium-ion is located in that region of the chart. Another key advantage of lithium-ion is the nominal voltage, which is considerably higher than comparable batteries such as nickel metal hydride, which is typically 1.2 volts. Lithium-ion has a standard nominal voltage of 3.7. Also, self-discharge is an important aspect. Basically, if the product's left in a not used state, how long does it retain its charge for? And as you can see, typically it only loses 5% around 5% in a month, compared to, say, nickel metal hydride, which is 30%. So, an overview of kind of the advantages and disadvantages. As we mentioned, it has a high energy density compared to other battery chemistries, such as nickel metal hydride. It has a compact package and size weight, which is brilliant for, obviously, portable consumer applications, but it also has advantages in larger applications because, obviously, you'd like to keep the power source to the smallest size possible, so it gives you the greatest flexibility in design. As I mentioned before, also low discharge rate compared to other rechargeable battery chemistries, which means it can be left longer and retain its charge. There are some disadvantages with lithium-ion batteries. Lithium-ion batteries are obviously sensitive to temperature, and because the chemistry tends to be a bit more complex than some of the traditional chemistries, more advanced protection is required against such conditions as overcharge, over-discharge, over-temperature. Also, because the chemistry is more active maybe than some other chemistries, more extensive testing needs to be done to ensure that the product is safe. Production costs tend to be, of the actual manufacturing of the cell, tends to be slightly higher than other chemistry types. Today, lithium-ion batteries can be found in a variety of industries and applications, ranging from consumer products such as a small battery pack used in a mobile phone to automotive applications such as a large battery pack in a hybrid car. As well as consumer and automotive industries, it's also popular in medical environments such as portable ventilators. It has military applications such as using in radios, bomb disposal robots, and also it finds its way into aerospace industry, powering satellites and providing auxiliary power for aircraft. The lithium-ion cell that is used in the actual battery pack can be found in three main types. The first type is the cylindrical, such as the 18650, which refers to the size of the cell and was the first lithium-ion cell to market. The prismatic was next to market, followed by the pouch cell, also known as the laminated cell. This cell has made a big impact in the cell industry due to the fact that the closure is flexible and is considerably slimmer and lighter than conventional prismatic and cylindrical cells. The general construction of the cell is very similar, except for the electrodes, which for cylindrical cells are jelly rolls when inserted into the enclosure, or the can, as it's sometimes known as, whereby prismatic and pouch, for example, tend to be in a stacked configuration before being placed in the end enclosure. The basic operation of the lithium-ion cell is once the cell is fully charged, the graphite anode on the left of the diagram will contain lithium ions. During discharge, these ions will then travel through the electrolyte to the cathode on the right of the diagram, which will result in current flow through the product that the battery is powering. When the cell is recharged, the opposite will occur. Current will then be forced in the opposite direction, and the lithium ions will return to the anode from the cathode on the right. The cell consists of three main parts, which are the electrode, the separator, and the electrolyte. The electrode in modern lithium-ion cells does not actually contain lithium metal due to instability during cycling. Today, the electrodes are in fact made from materials such as lithium carbonate, which is for the cathode, and typically for the anode would be made of graphite. The selection of the electrode material is important for capacity, so to maximise capacity, the voltage, energy and power capability of the cell. So it's a key selection point. The second key construction area is the separator. The main function of the separator is to isolate the positive and the negative electrodes and to retain the electrolyte, so the ions can flow through the separator on the basis that the separator is semi-porous. The separator is very thin, but it needs to be resistant to puncture by burrs on the electrode plate and has to have good insulation properties, mechanical strength, chemical and thermal stability. The electrolyte is an organic solution, or solvent, which is often lithium salt rather than water-based electrolyte, which is used in other chemistries such as alkaline cells. And this has basically the function of carrying lithium ions and so producing current flow. It is a highly conductive solvent which has a high temperature range. So a key difference between an electrolyte in a lithium-ion cell and one that's in say an alkaline cell or a nickel metal hydride cell is because it is an actual solvent, it has the potential to be highly flammable when it comes into contact with air and has the potential to release a lot of heat. Often you'll hear the words lithium ion and lithium ion polymer. So the question is what is the difference between these two types of cell? And basically it's the electrode, which the electrolyte, which tends to be in a polymer cell is more of a gel, so has minimum liquid, which has the effect of reducing the potential for flammability. And also it's often used in pouch cells, and as mentioned before, this enhances the flexibility of the cell over traditional cell manufacturing processes. Lithium-ion batteries have had negative press, particularly during 2005 and 2008 time, when relatively high incident rates occurred, resulting in fires and explosions. This resulted in costly product recalls for major manufacturers, which ran into millions of pounds. These type of incidents also have the potential to damage company reputations, which take decades to earn but days to lose. In extreme cases, it could be possible that legal action could be followed if due diligence could not be shown, that consideration has been given to the potential danger and appropriate measures taken to demonstrate the product's safe. So there's been lots of, over the few years, a lot of the public has seen negative stories relating to the production of lithium ion. So as stats show from the FAA, which regulates American aircraft, that between 1991 and 2011, there have been 118 incidents relating to batteries. And this basically just covers America alone, or American registered aircraft. So you can see that there have been quite a few incidents. So what are the reasons behind these incidents? As there's a lot of pressure on the cell and battery manufacturers to increase capacity and reduce size, there's a lot of design pressure on the design tolerances of the cell or the battery pack. Many of the high-profile incidents involving laptop computers in 2006, 2007 were linked to potentially inadequate manufacturing procedures, whereby contaminants were introduced into the production process. These were metal particles which penetrated the separator and caused an internal short circuit between the cathode and the anode, which resulted in thermal runaway. Another area of concern for manufacturers is the use of non-genuine batteries and chargers. Consumers are always tempted by cheaper, lower pricing. So when their battery is faulty or their charger no longer works, they will find an alternative part that may not be recommended by the manufacturer without realizing what the real safety implications are. And also, people tend to try to use chargers and maybe batteries that are not actually intended for the application. Also, as I mentioned before, protection circuitry is very important on lithium-ion batteries. So sometimes it can be caused by inadequate charging or protection circuitry, either in the end product itself or the actual battery. So how do you select an appropriate battery standard to test your product against? There are a number of things to consider. First off is the actual chemistry of the cell itself. A lead-acid battery will obviously tend to be tested to a different standard than an alkaline battery. And also another issue is the classification of the battery, whether it's rechargeable or non-chargeable. This will make a difference. So for example, if you have a portable lithium-ion battery, that will be tended to be tested against IEC 62133. Whereas if you had a portable lithium metal battery, that tends to be tested against IEC 60086-4, because that's a non-chargeable battery. Also, end application makes a difference as well. So if you have a lithium-ion cell that's used in a consumer product, a portable consumer product, again, IEC 62133 would be applicable. But if you were going to use a lithium-ion cell in an electric vehicle, appropriate standard maybe to consider would be IEC 62660. Another important area is the target market. So if you need to know which country your product is going to be sold in. So for example, if you sell your products in America, often UL standards are applicable rather than IEC or EN standards. Also, some countries have particular legislation that needs to be adhered to. So for example, in Japan, certain types of batteries need to comply to the Japanese PSE certification requirements. Also, some industries have their own requirements as well. So for example, in America, GSM and 3G network operators require portable cellular products such as a mobile phone and their batteries to meet CTIA requirements, which is a trade organisation. And the testing that is undertaken for this type of certification is based on standards such as IEEE 1625 and IEEE 1725. Another key point to distinguish between standards is often the standards are split between product safety or abuse testing and performance testing. So it's always worth having in your mind what your objective is to the testing. So are you solely concerned with safety, performance, or both? So quite often you will find there are two standards for your particular type of device which cover these two areas. It's also important to think of the complete system. So as we mentioned here, if you look at the diagram, on the left you can see the bare cell. So often that would be tested against the UN Manual of Tests. For worldwide access and European access, it would be tested against 62133. And if you wanted to also sell your mobile phone product in the States, UL 1642 would be applicable. Moving on to the complete battery pack, again the UN Manual of Tests would be applicable, as well as IEC EN 62133. But this time, the appropriate American standard would be, for example, UL 2054. And then you have the end product. When you get to the end product, you need to think of the integration of the pack into the end product, such as the mobile phone. So again, the mobile phone would be tested against IEC 6950 or UL 6950. And the testing in the end product, as well as would mainly more centre on the interaction between the phone and the pack. So it would check that the correct charging algorithm would be initiated, so it checks that the correct charge voltage and charge current are applied at the correct point, and this would be checked in the 6950 standard to see that it meets the pack specification. So another important point to make is when you're designing your end product is to make sure that your end product specification ties up with the cell specification and the pack specification. This diagram shows basically common modes of failure for lithium-ion batteries that should be considered when designing your battery and also the end product itself. One of the failure modes are internal shorts in the cell. These are difficult to control once they occur. Internal shorts are generally caused by such things as poor cell manufacturing process that allows small metal particles into the production process, and that has the potential to penetrate the separator. Also, other manufacturing defects such as poor electrode alignment or cell tab insulation, which basically, if this isn't correct, also causes short circuits. Dendrites, which are metal fibres that form on the carbon anodes, are caused by poor fast charging or discharging, so basically excessive charging above the limits, and this has the potential to compromise the separator material. So basically these metal fibres form on the anode, and basically because they grow on the on the anode basically eventually puncture through the actual separating material itself, so causing a short circuit between the anode and the cathode. Also, impact, which could be impact which could be maybe caused by crushing, which could occur maybe if an electric vehicle is involved in an accident, or even something as simple as if a mobile phone battery is dropped on the floor. Basically, this can disturb the inside of the cell and cause short circuits. Operating the battery in extreme external conditions, whether it's hot or cold, can also cause chemical imbalance, which can cause, for example, gas buildup, an increase in internal resistance, an increase in internal resistance, an increase in also internal temperature, which can result finally in thermal runaway. To the right side of the diagram, you can see possible end scenarios such as venting. Venting, to a certain extent, is a desirable result if, say, there's a tense build-up of pressure, because basically this means that the pressure within inside the cell can be released in a controlled manner, which will not result in an explosion. But obviously, you need to design your battery and the end product carefully, because obviously you don't want venting to regularly occur. This would obviously only be in extreme situations. And basically the main things that we don't want to happen to our battery pack are such things as rupture, whereby the actual enclosure splits and the internals of the battery are exposed. So this could result in electrolyte leakage, which is corrosive, and which is an corrosive substance, which is obviously not desirable. In worst cases, obviously fire can occur, and the worst possible scenario, an explosion could occur. So basically this identifies the fact that you need to design protection circuit carefully to minimise this potential hazards occurring. A lot of the tests in the standard are similar, with maybe minor variations such as the length of the test or the temperature at which the test is performed. Some of the common tests that you will find in battery test standards for safety are such tests as short circuit, abnormal charging, discharging, and vibration testing. Some standards, however, have particular tests that are not so common, such as, for example, SAE J2464, which is an automotive standard, and this has some particular tests that are relevant to the automotive industry, which include the penetration test, whereby a 3mm steel rod is used to penetrate right through the cell. And basically what they're looking for here is does the cell just vent and maybe catch fire, or does it actually explode, which probably wouldn't be a desirable effect. Another test that the SAE standard includes is a test called the rollover test, whereby a module, which is a collection of cells, or a complete pack, which is a collection of several modules, is slowly rotated in 90-degree increments and held for 1 hour. And basically what they're looking for in this test is basically any leakage, electrolyte leakage, to make sure that the end enclosure is firmly sealed to prevent any undesirable electrolyte leakage. Other standards that could be, other tests that are performed are, for example, EMC tests. These tend to be tested for more complex circuits. So for a basic mobile phone battery, for example, you may just only do an ESD, electric static discharge test. But for more complex battery packs, such as ones that are used in electric vehicles, a more stringent and detailed EMC tests are required, such as radiated immunity and emissions. So basically, does it generate emissions? Is it immune to its surrounding emissions that might be present in the car, which can be quite complex? There's also more performance-related tests, such as life cycle testing, as I mentioned before. So check how well the battery pack lasts under continuous use. So sometimes it may be the case that, especially in the automotive industry, whereby they have test profiles of typically charging and discharging under braking, acceleration, stopping. And basically this gives an idea to the design, gives a good feel to the design engineer that this battery pack product would be suitable in a real world environment. An example standard what we have chosen today is the UN Manual of Tests. This is a good standard to look into because this is required irrespective of the end application, or if it is a battery or a cell, or whether it's primary or secondary. The standard is essential to help demonstrate that your cell or battery is safe for transportation and applies for whether it's being transported by land, sea or air. And it's required by such organisations as IATA or IATA. Basically, this applies whether it's a primary or a secondary cell or battery. It's recommended that if you are designing a battery pack, is to source cells that already meet the UN Manual of Test requirements. Because basically, this minimises the testing that you have to do on the pack, which obviously saves you time, but also money. The scope of the UN Manual of Test is quite wide, so it applies from anything from a little coin cell that you might find in your watch, right through to EV, electric vehicle modules. The UN classifies dangerous goods into basically 9 categories, with lithium metal and lithium ion cells and batteries falling into category 9. Category of class 9, category 9 is basically a catch-all category for goods that do not fit into other categories, such as UN class 1 would be explosives such as dynamite, whereas class 7 would be something like uranium for radioactive material. So basically there's lots of different classifications for UN classified dangerous goods, and lithium metal and lithium ion falls into class 9. For compliance to UN requirements, lithium batteries are classified as either lithium ion or metal, and also an important aspect is how they are transported, whether they are transported on their own, whether they're fitted into equipment, or whether they're actually packed with equipment. The UN requirements, such as UN 3480, are then referenced out to what's known as packing notes, for example, 965. And basically these they apply for the type of transportation. So in this instance, the packing note refers to air transportation. Basically, for air transportation, the packing notes have basic common general requirements. So the requirement is that it must actually meet the UN Manual of Testing criteria. Waste batteries being transported by air for recycling and disposal are not permitted unless approval is sought from the country of origin and the country of the airline operator. Cells that are defective in terms of safety returns, so there's a safety problem with the cell or battery, are forbidden for air transportation. Also, the battery or the cell must have be protected from short circuits. So this could be within the actual battery pack itself, but also the material. So it must be securely packed in packing material, and consideration must be given to the fact that this must not be conductive packaging material. When packed within equipment, the general requirement is that accidental activation must be prevented. So if you are transporting, say, a rack system or something like that that has batteries in it, it's best to isolate the battery. If it's embedded into the actual product itself and it has an on-off switch, it's quite a good idea maybe to design packaging that prevents the switch from accidentally going on to the on position. The packing note is basically divided into two categories, which are regulated class 9 and exempted. Exempted basically is classified as cells that have a rating of less than 20 watt-hours for a rechargeable battery, or for a primary cell, it would have a lithium content of less than 1 gram. For batteries, it would be for rechargeable less than 100 watt-hours or less than 2 grams lithium content. In this case, there would then be less stringent packaging requirements. So basically, the main requirement in terms of packaging for exempt would be that once it needs to be packed, obviously, in strong packaging material. And then basically the package, including the cell or the battery inside, would then be dropped from 1.2 meters. And basically this would result in no damage to the contents or shifting of the contents that allows contact between the cells or packs, and also release of the actual contents of the package. Class 9, which is obviously the more hazardous type of product, basically must have a safety vent present and be packed in class 2, what's known as class 2 packaging. Basically class 2 is classified as a medium danger, class 1 is a high danger, and class 3 is low danger products. The UN transportation requirements require clear labelling of the packaging, detailing what's actually inside, warnings for safe handling for handling crews at the airport, for example, and identification of any potential hazards. The exact label requirements are detailed in the particular packing note, so it's always advisable to actually read the packing note that's applicable to your product. Certain countries, couriers and carriers have additional labelling and documentation requirements, as well as weight limitation and restrictions that are in addition to the basic UN requirement. So again, it's always worth discussing with your airline or courier if they have any additional requirements other than those detailed in the UN requirements. For example, in the United States, lithium metal batteries or cells are prohibited for transportation in passenger planes. So the orange label to the right should be affixed to the packaging of lithium metal batteries or cells. And basically this is detailed in the US Department of Transport's 49 CFR regulations. And this is again detailed in the UN's country deviations under USG02. Lithium metal cells or batteries can be fitted in the actual equipment or packed with equipment and are permitted for transportation on passenger aircraft which are bound for or within the US under certain restrictions, such as a limitation of the actual lithium content of the anode for primary batteries, and also no spare batteries are allowed to be packed within the equipment too. The UN Manual of Testing Criteria is set out as a set of 8 tests covering environmental, mechanical and electrical tests to demonstrate compliance for safe transportation. The tests are often known as T1, T2, T3 tests. So for T1, that would refer to the altitude test. Tests T1 to T5 are applied to all types of lithium cell and batteries, whether they are primary or secondary. Tests T6 and T8 are only applied to actual cells, and T7 is only applicable for rechargeable batteries. Revision 5 of the UN Manual Testing Criteria came into force at the beginning of the year and mainly addresses the use of lithium-ion batteries and lithium batteries in large applications such as electric vehicles. So basically it introduced some new classifications. So it introduced the classification large cell, which for a lithium-ion battery would have a rating of higher than 150 watt-hours, and if it was a lithium metal cell, it would have a lithium anode content of greater than 12 grams. It also introduced the large battery category, which is any battery that has a gross weight of more than 12 kilograms. Battery assemblies, it classifies large battery assemblies for lithium-ion as anything greater than 6,200 watt-hours, and for lithium metal primary batteries, lithium anode content of greater than 500 grams. So what is the significance? Basically, for rechargeable larger batteries, less test samples are required. Limited testing is required for small battery assemblies, so only one sample is required, and limited testing on that one sample would be the T3, T4, T5 and T7 tests. If the cells and batteries that are used within the assembly pass all the relevant tests. So basically the cell or battery that is used in the battery assembly still needs to meet all the relevant requirements. It's only the end battery assembly that the limited testing is performed on. Also, for large battery assemblies, such as battery packs that are used in EVs, there are no test requirements if the EV battery module has passed all the tests, as long as the actual large battery assembly is monitored by a system which prevents short circuits or over discharge conditions, as well as overheating or overcharging conditions. So basically it means if the modules used inside your EV battery pack have been fully tested and you have a battery management system that prevents short circuits, that you do not have to actually do any testing for the UN manual of test for the actual battery pack. This table basically shows the sample requirements for tests, and it depends on whether it's a cell, a battery, and if it's a primary or secondary cell or battery. Tests 1 to 5, or T1 to T5, are performed on the same samples, but for tests T6, T7, and T8, a different set of samples can be used for each test. For prismatic cells, an additional 5 samples are required for the impact test, T6. So basically this is required because 5 samples will be tested along the longitudinal axis, and another 5 samples will be tested along the other axes when the impact is applied. For larger rechargeable batteries, which are more than 12 kilograms, only 4 samples are required instead of the 8 for batteries that are under 12 kilograms, as indicated by the red text, and the samples are only cycled 25 times rather than 50 for the smaller battery packs. Okay, so the first test, as mentioned, was T1, which is altitude simulation, and basically this is a low pressure altitude test that evaluates the ability of the cell or the pack to withstand conditions within, for example, a cargo hold at 50,000 feet. The test item is placed within the chamber at 11.6 kilopascals for 6 hours at room temperature. And basically the requirement is that the sample must not catch fire, it must not disassemble. In the context of the UN Manual of Test, disassemble means venting or rupture, which results in solid matter passing through a wire mesh. So basically when this test is performed, it's enclosed in a wire mesh, and if it disassembles and solid matter passes through that metal mesh, it's classed as a failure. Also, it mustn't vent. So basically venting means controlled release of pressure from the cell through the cell's vent mechanism. The requirement is no mass loss. So the UN standard requires the mass to remain the same after test as it was before test, and there's quite a tight tolerance. So, for example, it mustn't lose more than 0.1% of the original value. Another requirement is it mustn't rupture, And basically this means a mechanical failure of the enclosure, which would expose the contents of the cell or battery. So that could include electrolyte leakage. The T2 test is the thermal test, and basically this tests the cell or the battery's seal integrity and also the internal connections when exposed to temperature extremes. Basically, these temperature extremes are maintained for 6 hours. So basically, the chamber is ramped up to 75 degrees and held there for 6 hours. Then it is lowered to minus 40 degrees. And basically, the transition between 75 and minus 40 is it must happen within 30 minutes. And basically, this is done 10 times. And then it's left at room temperature for 24 hours before the pass criteria is evaluated. So again, no fire, disassembly, leakage, venting, mass loss or rupture must occur. And again, the open voltage must be within 90% of the pre-test voltage. Next test is T3, which is the vibration test, and basically this is to replicate or simulate vibration that could occur during transportation. And basically the sample is clamped securely without influencing the test onto the test table that you can see on the right. And basically it's swept through some frequency ranges, so it starts at 7 Hz and rises to 200 Hz and back down to 7 Hz in a 15-minute duration. This test is repeated, this cycle is repeated 12 times in 3 hours, and basically it is repeated at 3 mutually perpendicular planes. One of those directions will be perpendicular to the actual terminal face. It involves peak accelerations of 1 g between the frequencies of 7 to 18 Hz and increases to 8 g between 18 and 200 Hz. Again, the pass criteria is the same: no fire, disassembly, leakage, venting, mass loss or rupture. And the open circuit voltage at the end of the test must be within 90% of the voltage that you measured at the start of the test. The T4 test is the shock test. Basically, this simulates the impacts that could occur during the transportation of the cell or the battery, Basically, this is a half-sine shock at 150 G for 6 milliseconds for small cells and batteries. That is decreased in terms of G force to 50, but the duration is increased to 11 milliseconds for larger cells and batteries. Basically, 3 shocks are applied in each direction and for 3 mutually perpendicular mounting positions to cover the X, Y, Z axis. So basically, a total of 18 shocks are performed on each cell or battery. Again, the pass criteria is no fire, disassembly, leakage, venting, mass loss or rupture, and the open circuit voltage must again be within 90% of the voltage, the pre-test voltage. The T5 test is the external short circuit test, and this is basically to represent a short circuit on the positive and negative terminals, which results in a high current being drawn. Basically, the test procedure is to place the test item in the chamber at 55 degrees, and the shorting method must create a resistance of less than 100 milliohms. So the shorting method isn't actually described in the standard, so it can be any method that you choose that creates a resistance of less than 100 milliohms. So, for example, it could be a high voltage current relay. The test duration is basically 1 hour after the enclosure temperature returns to 55. So basically, this means that the battery is placed in the chamber. You monitor the temperature, and as soon as the enclosure of the cell or the battery returns back down to 55 degrees, that's the end of the test after 1 hour of that occurring. After that, you observe the test sample for 6 hours, and you check for the pass criteria of no fire, no disassembly, and no rupture. In this case, it is permitted to for the battery or cell to vent. During the duration of the complete test, the case temperature must never exceed 170 degrees. Next test is the impact test, and this basically applies to cells only. Basically, the cell is positioned on a flat surface, and basically a metal bar is placed across the cell. Its diameter is 15.8 millimeters. Then a 9.1 kilogram weight is dropped from a height of 61 centimeters onto the cell. It's only one impact per cell. Basically, 6 hours after the test, you check that there is no fire, no disassembly, and during the course of the test, obviously there should be no fire or disassembly, and also during the entire test process, the cell enclosure must not exceed 170 degrees. The next test is the T7 test, which is the overcharge test. This is basically to test the ability of the pack to withstand an overcharge condition. So you basically need to check the manufacturer's specification. So basically the test method is to set the charge current to 2 times the maximum recommended continuous charge current of the pack. The voltage is set to either 2 times the manufacturer's recommended continuous charge voltage, or 22 volts, whichever is the lower of the two. If the rated voltage or the rated recommended continuous charge voltage is greater than 18 volts, the test voltage ratio is reduced to 1.5 times rather than 2 times. Again, the test duration is 24 hours. After 7 days, a visual inspection is performed, and basically during the test and at the completion of tests, no disassembly or fire shall occur. The T8 test is known as the forced discharge test. Basically, this is to evaluate the ability of a discharge cell to withstand a forced discharge condition. Basically, the cell is connected to a 12-volt power supply with appropriate load resistor. How you calculate what the appropriate load resistor should be is basically the load resistor should be appropriate for the should be appropriately rated for the test. So it should be rated for 12 volts and the maximum charge current as specified by the cell manufacturer. The actual duration of test is basically calculated by dividing the rated capacity in amp hours against the maximum discharge current in amps. Basically, after the test, it's left for 7 days, and after the 7-day period, a visual inspection is performed to check that no disassembly or fire has occurred. So these tests are quite extensive, and as we mentioned previously, the chemistry of lithium ion has the potential to be quite volatile. So safety features are required in the battery pack and the cell. So the first safety feature would be a vent or a vent plate, and basically what this does is it when excessive build-up of pressure is inside the cell through abnormal heat generation or overcharging, for example, a vent is present that allows the safe release of gas, which is shown in these diagrams here. The one to the left relates to cylindrical cells, and the one on the right is a prismatic pack, which shows the exhaust valve or the vent plate. Another safety feature that's often used is the PTC. This acts as both a current fuse and a thermal fuse, so that when excessive current is drawn, resistance of the PTC increases, resulting in heat generation. Resistance of the PTC is selected so that it trips a predetermined current. So again, you need to look at the specification of both the cell and the pack to ensure that an appropriate trip current is actually specified for the PTC. We mentioned earlier on the separator, which had the important function of separating the anode and the cathode. It also acts as a safety device too. When the separator reaches a defined temperature, typically 130 degrees, the pores are blocked by the melting of the material, so this prevents current flow between the electrodes. Sometimes the separator is known as the shutdown separator. When thermal runaway occurs, quite often the temperature is so extreme that the actual separator actually melts or shrinks, which then allows the two electrodes, the anode and the cathode, to actually come into contact with each other. A thermal fuse device is quite often used in prismatic batteries. This is an additional feature, and basically the prime function of the thermal fuse is to limit the current under a fault condition such as a short circuit. As I mentioned earlier on, protection circuitry is a key safety feature of a battery pack. Basically, this battery pack, this PCM or protection circuit module, basically is a typical circuit that would be used for a one-cell battery pack. And basically, the idea is basically the control IC monitors the cell and prevents overcharge conditions. So basically, most cell manufacturers recommend that you don't charge beyond 4.3 volts or around that 4 to 4.3 volts. So basically, you specify an overcharge voltage limit based on the cell specification. It also has an over-discharge function, which is typically, say, 2.5, 2.7 volts, whereby the manufacturer of the cell recommends you don't discharge below that value. Overcurrent protection is also provided in the form of the PTC. The combination of the two FETs basically controls the charge and the discharge. There's also typically a temperature sensing device, which is normally a thermistor, which is basically there to ensure that the charging doesn't occur over a set temperature. So the charging IC will then shut down the charging function to prevent overcharging or charging at excessive temperature. For more complex systems that involve multi-cells, more complex systems required, which is basically a battery management system, which maybe includes communication protocols such as SM bus or CAN, which basically means there's data transfer between the pack and the end product to ensure that these parameters such as overcharge, over-discharge are kept within parameters. It also does things such as voltage sensing, so it basically monitors the voltage of individual cells within the battery pack to make sure they aren't excessively charged or discharged in an individual basis. Basically, there are many aspects to consider when designing power management or protection circuitry. One of them is ambient temperature, to make sure that you check that the charging and discharging is prohibited in excessive temperatures, whether they're high temperatures or low temperatures. Another thing to consider is also radiated heat from components in the proximity of the pack. So if you know there's a particular hot area in your design, it's best to locate the battery pack well away from those areas. As mentioned before, you need to have overcharge, over-discharge, over-current protection, as well as over-voltage protection. Another design feature that is important is algorithm design. So basically, are the correct voltages or current supplied at the correct stages of the charge cycle for the correct duration of time and under the correct conditions. So some battery systems may have a trickle charge function. So the algorithm will dictate when this trickle charge, which is basically low current charging, basically occurs. So basically trickle charge is when it goes down to the very low limit of the specification, it trickle charges up to a certain limit, and then the algorithm will then initiate the full charge sequence. Another area to consider is short circuit avoidance. So it's basically to minimise accidental short circuit, maybe the detachment of wires in the proximity of the battery, separation distances between tracks and pads on the PCM or surrounding area to make sure that there's no short circuit occurrence. Another thing is leakage protection. It's basically if the battery cell leaks, the electrolyte that's present is corrosive and conductive. So if there's no segregation between the cell and the protection circuitry, you've got the potential for the electrolyte of the cell to corrode or create short circuits on the protection module, and so defeat the purpose of it. As we mentioned earlier on, the cell vent is an important design feature to let the release of gas under fault conditions. It's important in the end application that this cell vent is not actually blocked or restricted, so a clear vent path needs to be created within the actual battery pack, which is typically important if you decide to pot your cell, use potted material in your cell in your battery pack design, and that you don't actually block off the actual vent. User instructions are also important. It's always important to educate the end user as to the potential risks and hazards that are involved. So appropriate instructions to reduce hazards to the user, and which might also result to damage of the product should it result in a safety hazard. For example, identifying the maximum ambient conditions of use for the product, identifying the correct battery charger or power adapter to use, and to give details of what the correct disposal of the product is at the end of its life. So, for example, not to place it in a compactor or something like that where it could get shorted out and crushed, or not to chuck it on something like a fire or something like that. So then there's obviously the explosion hazard. As mentioned before, multi-cell packs are obviously more complex, so they need more advanced battery management systems to control higher voltages and current. Often this involves individual cell monitoring of voltages and stuff like that. And that tends to use more complicated control language such as SM bus and CAN protocols. Basically, it's good to remember for the robustness of the design, it should be verified under normal and fault conditions. So you have basically a robust design which covers, as well as performance, the actual safety of the product.